Hello viewers, I once again extend a very hearty welcome to all of you in this new session of my discussion on the topic of salt analysis. In previous sessions, in previous lectures, I started the discussion on acid radicals. Various preliminary tests for the detection of acid radicals were to be covered in this topic. And in the previous lectures, I discussed general introduction of salt analysis, then dilute H2SO4 test as one of the preliminary tests for the detection of certain acid radicals, and then confirmation of those acid radicals which were detected with concentrated dilute H2SO4 test, they were confirmed. Now, before proceeding further for the confirmation of acid radicals with the acid radicals which are detected with the help of concentrated H2SO4 test, I would like to discuss with you people another small but important test, preliminary test, that is KMnO₄ test. This test is performed after we perform the dilute H2SO4 test, because we come to know about if some radical is present to be detected with dilute H2SO4, then we come to know about that, and then we proceed further to detect some of the acid radicals which are to be confirmed subsequently, indicated subsequently with concentrated H2SO4 test. They give an indication in this KMnO₄ test. Usually, the radicals about which we get information with this test are chloride, bromide, iodide, oxalate, tartrate, and some basic radicals which have oxidizable cations. For example, Fe2 positive, SN2 positive, etc. So regarding these radicals, we get some indication with KMnO₄ test also. Now, as I told you that we have to perform this test after dilute H2SO4 test, so what we do is we check whether some radical to be detected with dilute H2SO4 is present in the mixture or not. If such radicals, that is namely carbonate, bicarbonate, sulfide, sulfite, thiosulfate, nitrite, etc., if they are present in the mixture, then first of all we'll have to decompose them, and then we perform this test. So what we do is we take about 1 gram of the given salt mixture. We add about a milliliter of dilute H2SO4 to it. If some radical to be detected with dilute H2SO4 is present, then we heat it. We heat the reaction mixture or we warm it so as to decompose it. Once the outgoing gases are ceased, that is, they cease to be emitted, then we add a few drops of KMnO₄ solution into it, and then we observe what is happening. There are the observations. Now, all of us know that KMnO₄ is a brownish blackish solid. When dissolved in water, it gives us purple solution. So how do we perform this test? To that solution from which the radicals of the dilute H2SO4 test have been decomposed, we add more of dilute H2SO4 and then about 3-4 drops of KMnO₄ solution in water. Now, there could be following observations. Number one, color of KMnO₄ is discharged one situation is with the evolution of a gas. And another situation is without the evolution of gas. Without the evolution of any gas. And third situation will be the color is not discharged. The color is not discharged. Now we shall be dealing with these situations one by one. Now, before proceeding to these situations, I would like to share with you that KMnO₄ acts as an oxidizing agent in acidic, basic, as well as in neutral medium also. But here we will be discussing KMnO₄ as an oxidizing agent in acidic medium. So as I told that to the salt solution we add a few drops of dilute H2SO4 and KMnO₄ solution is added to it. Now, how the underlying chemistry is, KMnO₄ in the presence of sulfuric acid will give following reaction. This is the base equation. KMnO₄, purple colored, in this forward reaction will give us potassium sulfate, manganese sulfate, water and nascent oxygen. But this reaction will happen only if some oxidizable material or if some reducing agent is present there. So this is a basic equation which we'll be discussing. So now I'll be discussing with you the situations one by one. The first situation, that color of the KMnO₄ solution gets discharged with the evolution of a gas. Now we'll have to detect from the observations, from the properties, that which gas could it be. So first case is evolution of greenish yellow gas which bleaches the moist litmus paper. So this greenish yellow gas would be chlorine gas, and this chlorine gas would be from a chloride. What is the chemistry behind? Suppose we have got this KCl. KCl on reaction with H2SO4 will give us 2 KHSO4 plus, of course, 2 HCl. Now, as I said, the basic equation, I would like to write basic equation here so that we are not required to write this equation again and again. So this basic equation is 2 KMnO₄ plus 3 H2SO4 gives you K2SO4 plus 2 MnSO4 plus 3 H2O plus 5O. This is the basic equation. Now, this HCl which is furnished by the reaction of given chloride, say KCl with H2SO4, now this will undergo oxidation now. 2 HCl plus nascent oxygen, this will give us, say, H2O plus chlorine gas, and this chlorine gas, greenish yellow gas, when moist litmus paper, which is blue in color, how it is prepared, we dip a filter paper cutting into the blue litmus solution, we take it out, we wrap it around a test tube in which the water is being boiling, then that filter paper cutting gets dried up, it's a bluish in color. And when that moist filter paper cutting having litmus solution, which is known as litmus paper, so when this moist litmus paper is brought in contact with chlorine gas, the litmus paper gets bleached. Litmus paper is bleached. So this indicates that chloride must be present in the salt, which coming in contact with acidified KMnO₄ bleaches the litmus paper. How? You see, this is a basic question. And I told earlier that this KMnO₄ is of purple color and it gives us K2SO4 and MnSO4. MnSO4, you know, is very light pink in color, but in dilute solution, it is almost colorless. So we'll write it as colorless. So this reaction will proceed in the forward direction only if this nascent oxygen is consumed. So this nascent oxygen is consumed by this HCl. This reaction goes in the forward direction and color of the KMnO₄ gets discharged. So this is how we are to confirm the chloride. Now second in the series comes bromide. I rub it here. So second option is that we get the evolution of orange yellow gas, which turns moist starch paper yellow. How? So this, suppose we have got a bromide with us, KBr, when comes in contact with sulfuric acid, will give us HBr, and this HBr consumes this nascent oxygen, gets oxidized to bromine. This is yellow brownish gas, and then this bromine comes in contact with moist starch paper, which is, you know, white in color, and when this comes in contact with this paper becomes yellow, forming a complex of bromine starch complex. So in this way we'll be getting an indication that bromide is present. Now third in the series is another halide ion, that is iodide. So what happens? Suppose we have got an iodide as Ki. This comes in contact with sulfuric acid, will give you 2HSO4, plus of course we'll be getting 2Hi. And this Hi again gets oxidized by the nascent oxygen furnished by the acidified KMnO₄, and this becomes water plus iodine. This is violet vapors. So when these violet vapors come in contact with moist starch paper, this becomes starch paper turns bluish, blackish, again due to the formation of starch iodine complex. So in this way, chloride, bromide, iodide radicals could be detected with the help of this KMnO₄ test. Now next in the series comes oxalate. In case of chloride, bromide and iodide, the color of the KMnO₄ solution was discharged with the evolution of colored pungent smelling gas. Greenish yellow in case of chlorine and reddish brown in case of bromide, and violet colored vapors in case of iodide. But in case of oxalate, you see, colorless, odorless vapors are evolved. Of course, there is no smell, and again the color of the KMnO₄ is discharged. This could be due to the presence of oxalate or tartrate, which in turn, in coming in contact with sulfuric acid, they form oxalic acid and tartaric acid, and oxalic acid and tartaric acid undergo oxidation with the nascent oxygen furnished by KMnO₄ to give carbon dioxide gas, which is colorless and odorless. So we take the example of oxalate. So number 4 is oxalate. Suppose we have got sodium oxalate that combines with H2SO4 to give you H2C2O4 plus sodium sulfate. And this H2C2O4, oxalic acid, coming in contact with nascent oxygen, and of course we heat it, we get the formation of water plus 2CO2. So this is the colorless, odorless gas evolved in this case, and in turn the color of the KMnO₄ is discharged. So I'll write this equation in a little better manner. So in this way, KMnO₄ changes into manganese sulfate, color is discharged, and the nascent oxygen is consumed by oxalate. Now, as I told earlier, that usually at this level we don't provide tartrate ion, so I am not going to discuss the test of tartrate. Otherwise, in case of tartrate also, tartaric acid on oxidation with nascent oxygen gave you, of course, carbon dioxide and water. So this was the first situation, that is, color of the KMnO₄ is discharged with the evolution of a gas. That gas could be having some color and some odor, and it could be odorless also. Now the second situation is that color of KMnO₄ is discharged, KMnO₄ solution लिख दो, is discharged without the evolution of any gas. This is the situation in which we have oxidizable cations. You see, these cations could be ferrous, it could be stannous, it could be even antimony, it could be lead, etc. So these are oxidizable cations, but usually in these cases the color, discharge of the color of the KMnO₄ is very slow, so that's why we generally don't consider these reactions here. We have got tin and lead, and I'll be discussing by taking the example of ferrous the mechanism of the reaction. You see, any ferrous ion present in the salt that combines with sulfuric acid to give you ferrous sulfate. This ferrous sulfate, in the presence of H2SO4, and consumes nascent oxygen to provide ferric sulfate. In this way, ferrous, has been oxidized to ferric. And as I told you earlier, that this reaction will be accomplished only if this nascent oxygen is consumed. So nascent oxygen is consumed, which is provided by the acidified potassium permanganate solution, and ferrous ion changes into ferric ion, and this reaction moves in the forward direction, and we get purple colored KMnO₄, we get this as, say, colorless manganese sulfate. So in this way, tin also, if tin is present, then stannous will change into stannic and so on. So this was the second situation, that color of the KMnO₄ is discharged, but there's no evolution of any gas. And the third situation is that color of the KMnO₄ solution is not discharged. So if the color of the KMnO₄ solution is not discharged, then the ions, that is which we indicated, chloride, bromide, iodide, oxalate, then ferrous, tin, etc., may be absent. So in this way, viewers, this is a small test, but this gives us indication regarding the presence of these ions, the chloride, bromide, iodide, oxalate, and these are the ions which in fact will be detected by concentrated H2SO4 test as a preliminary test, and subsequently they will be confirmed by their confirmatory tests. Similarly, these cations, if indicated in this test, then of course while doing the analysis of the cations, we can further confirm the presence of these cations. So I hope this small test would give you an insight into the analysis of these ions, and this gives an indication, and the account which we have discussed today, that will definitely help you in understanding the chemistry behind the KMnO₄ test. Now in our subsequent discussions, we'll be discussing the concentrated H2SO4 as concentrated H2SO4 test as a preliminary test, and the radicals which are detected by concentrated H2SO4, they will be confirmed by confirmatory tests. And then of course there are certain radicals which are detected neither by dilute sulfuric acid test nor by concentrated H2SO4 test. They are detected and they are confirmed with individual tests. So with that, we'll be completing our series on analysis of acid radicals in a salt mixture. So thank you very much for watching this, and please stand by for the next sessions whenever we meet next time. Thank you so much.